in simulation, no, CST simulation, whatever we are seeing is like, for example, you have a unit cell like this, okay? Unit cell like this. It can have a, ground plane or without ground plane also. So with ground plane, with ground plane, I mean to say reflector, that's all, okay? So reflector is there means I will measure the S11, okay? And if there is no reflector, it's, for example, transparent frequency, selective surface or transmitter kind of thing. I will measure S21 or S12, okay?
Yeah.
Those things I will measure, right? So here I am going to, so in order to evaluate this unit cell performance, okay, there are, what and all I have to measure. One is S11 amplitude.
Yes.
For example, in the case of reflector A or reflecting unit cell element, I have to measure both S11, we have two components. One is amplitude and phase, okay?
Yeah.
There are two components basically. One is amplitude and phase. So amplitude, what you infer in S1, no? In the amplitude, what you get infer? One is that, for example, see, your signals are getting impinged on this unit cell, and then it is passing over here and then getting reflected over here. Okay. So what happens is, see, it is getting just impinging on the unit cell, where you have, for example, it can be like this. For example, this is the substrate. You can have a patch like this. Okay.
Yeah.
For example. So it just signal is getting impinged on this, and then it is passing through the substrate. There, where it is a dielectric, right? As it is a dielectric, it will experience some kind of losses, right? Then it is coming, it is hitting on the reflector or ground plane. Then it is coming back. So it is again experiencing the losses, okay?
Mhm.
And the reflector also, it is not a perfect electric conductor, right? It's not an ideal conductor. It will also, during the reflection, it will also causes some kind of losses. So these losses can be accounted in this, for example, amplitude. So in the CST simulation results, when you look at the amplitude in terms of dB, you may get, for example, minus 0.0404 dB, 0.42 dB, 0.2 dB, like that. Or if you talk in terms of magnitude, absolute value, you will may get a 0.96, like that. Which means, for example, 0.04%, 4% you are getting, getting lost, and 96% you are getting, completely getting reflected back. So the 4% loss of signal you are getting. So this is how we quantify for the amplitude perspective. In phase perspective, what we have to see is that, see, in some of the videos also I might have mentioned these things. Like, what happens, see, ideally what is happening is, so your incident, you are impinging the, let me, 1 minute.
So what I'm thinking is like in terms of the phase, if I design a material that has quite different phase responses based on the graphene,
Exactly. Exactly. So
I'm
yeah,
using.
yeah,
Uh,
yeah, that's what I'm coming over here. See,
uh-huh.
like, for example, see, you have a, for example, see, you have a material like this, okay? You have a, a reflector like this, ground plane, for example. You have patch like this, okay? So, so, so this has some dielectric constant, right? Epsilon r, correct?
Yeah. In
Yeah,
the materials, they use, like, for example, silicon dioxide as a substrate. Uh, and I'm
yeah, yeah.
using in
Any
CST,
material.
in
It can
CST,
be
for
any
example, I'm
material,
using
okay?
the
So,
lossy silicon. Would that be okay?
yeah, yeah, that can be any material, okay? So,
Yeah,
what I'm trying to say is, for example, in the air, it is going to be 1, correct? In
yeah,
the air, it is going to be 1, okay? So, what happens is, see, lambda will become lambda naught in the air, okay? Lambda naught means, so
yeah,
where you are having lambda, epsilon r is, going to be 1. But it is in the, for example, when a wave propagating in the free space, okay, so your lambda going to be lambda naught. So and velocity will be still remains the same, but when it sees the medium, so for example, velocity, how we measure, so square root of epsilon naught mu naught, you will get this value, correct? Free
correct,
space velocity, correct? Correct.
correct,
So
yeah,
now, the moment it enters the medium, the moment it enters the medium, so why here it is epsilon naught mu naught? because epsilon r value is 1. So the moment it enters the medium, what happens? Velocity gets changed, right? Epsilon naught, epsilon r, mu naught, correct? So the velocity is getting changed. Therefore, what happens is, what is lambda? You have c by, yeah, okay. So the velocity is getting changed. So I'm saying that this wavelength is called as guided wavelength. Okay, this wavelength is called as guided wavelength. So lambda g is equal to, how we can represent c is what? The what is so you can see, you can split this square into two things, epsilon naught mu naught multiplied by epsilon r, right? So what will happen? C by epsilon r. You can just decode it to C by epsilon r. So lambda g will become lambda naught divided by square root of. So see, when it is a wave propagating in the free space, it will have some kind of propagation velocity. And the moment it enters the medium, the velocity is getting changed. Correct? Velocity getting changed because of this. And also guided wavelength will get changed. Okay, guided wavelength is getting changed, which means, in other words, you can say frequency is getting changed. Okay. In other words, you can say, for example, your LC component is getting changed. So I'm coming one by one. For example, see, when the wave propagating in this free space, you will not find, any dielectric medium is epsilon r equal to 1. Therefore, you will see some wavelength remains lambda naught only. The moment it enters the medium or in a substrate that has a more than one epsilon r. Okay, what happens is the guided wavelength will come into picture where the velocity is different. Okay, so when the guided wavelength is different, then frequency also different. So frequency is different means, in other words, it is changing the L and C. So these L and C components are causing the phase. Okay, because these are all, we can say, if you take a complex impedance value, it will be R plus JX, right? So if you write in terms of amplitude, so for example, you can write like this, right? J something like that, right? Correct. So here, these term, whatever the terms that is getting changed over here, when you have a zero LNC component, there is no phase shift at all. Then what will happen? This term will go, you will get only magnitude, right? So, but when you are having non-zero value, then what will happen is this term is going to come, phasor term is going to come. So therefore, these phases getting changed. Okay, correct.
Correct. Yeah.
So when it gets to medium, so what is happening? The phase is getting changed. Okay, so basically, so for example, in this particular patch, so for example, see, there is a, in 1940s itself, they have created some kind of artificial dielectric. Okay, so what they have done is, for example, you have a dielectric medium like this, okay. Here what they have done initially, they have had a dielectric hole like this. Okay, they made a hole like this. Okay, hole like this, by controlling the diameter and the spacing between the holes, they have controlled the overall effective dielectric constant of this particular material. Okay, effective dielectric constant of the material. The complement of this will be, you will not have any material, you will just have a metallic posts. So here it will be via holes, but here you will have metallic posts. So the gap between them is, it's going to be air basically. So this also cause the variation in the dielectric constant, effective dielectric constant. So why I'm calling it as effective dielectric constant? When you have a effective dielectric constant like this, when you are controlling this parameter, indirectly what you are doing, you are controlling the frequency as well as the LNC, because LNC is represented in terms of J omega something like that, right? J omega F like that, right? So sorry, it's a sorry, J omega something like that, right? Therefore, what you are doing, by controlling this effective dielectric constant, what I am controlling indirectly, I am controlling the frequency to be passed or not passed or getting reflected with some phase, which means LNC I'm playing a role, and therefore I can control this phase as well. Okay, apart from this magnitude. So that is what is happening here. So here what I'm doing, you have a patch. So that patch, no, see this dielectric material is not uniform, right? Obviously, because you have a patch over here, correct? Okay, so within the dielectric medium, you have a uniform material. But if you look at this perspective, this overall perspective, you are not having uniform dielectric, right? There is a patch over here, metallic over here. This will create some kind of offset in the, for example, the effective dielectric constant gets changed. Therefore, when the dielectric constant change, frequency changes, LNC changes, phase will change. That's what is happening. Now, coming to your doubt, of how why we are using CS to measure that. Now, I need to quantify this. For example, you have a
By the way, sorry to disturb,
substrate,
but I think the
ground plane. So what I'm getting, see, in CST, what we are going to do is that, so we are going to excite a plane wave here, okay? We are going to excite a, so that is what, you're in Floquet port, what you are doing, you are going
yeah.
to excite a plane wave here. It can be a single polarized or dual polarized, anything is fine. So that is what you call it as Z max, okay? You are going to excite this port. Next, you have AC. You can have another port here also. For example, if you are having a
That
frequency selective surface or transmitarray unit cell, no problem. So you can have another port here, Z min. It is going to be Z min. If you talk in terms of S parameters, right, it's going to be, this is port number one, this is port number two. If you want to measure S11, it is going to be S parameters, Z
that's fine.
max, Z max. You are talking in terms of S22. Okay, then it is going to be yes, Z min, Z min like that. Okay. Now, if you want to cross function, like coupling between these two, then you are going to talk about Z max, Z min like that. Okay. So now, so I have to analyze. For example, let us take this reflector, the reflecting surface. So there, I no need this. Either if you configure this port or not, doesn't matter, because you are going to have a plane. If you are having full reflector here, it doesn't matter. Either you
Yeah.
configure this or not, doesn't matter, because you are not going to get anything over here. So what I'm going to do is, see, I'm going to excite the plane wave here. I'm see at this port, no, the distance between these two will be lambda by 4. Why lambda by 4? So when you look at the sine wave, okay, so this is 0 degree, this is 90 degree, this is 180, 270, and 360, correct? So if I keep lambda by 4 distance, which means what? I'm going to experience 90 degree, correct? There's a wave, that is starting from here. It's going to experience 90 degree phase shift, correct? So 90 degree phase shift, it is coming over here, 90 degree phase shift. Then the reflector, no, I will introduce 180 degree phase shift. Then it is coming back. So 90 degree phase shift. Okay. So total 360 degree. You will not find any offset here. So distance to reference plane. So which means what? Distance to reference plane. Which means what? Means, see, this is the port where I have to estimate the phase. Where I have to estimate the phase. Either I here, here, here. That is what is the distance to reference plane. Okay. So distance to reference plane is, for example, again, we can keep it as lambda by 4. So which will fall exactly here. Okay. So which means, so while I'm sending the signal, it is getting reflected back. Here I'm just evaluating that how much phase this unit cell is generating. That is what I can expect. Okay, this reference plane, no?
Yeah.
If you, I say you can change it. Say in some scenario, no, you can place it over here, reference plane. So there exactly what is the phase I'm getting here. That is why we are putting it as, for example, if you talk in terms of here, it will be minus something, because you are going to move your reference plane to from here to here. That's why you are putting, for example, lambda not 5, 4 value, the equivalent value in the port settings, right? That is
So
what is the one.
so
That's
that
all.
would be only for just one frequency though, lambda by 4. So if you're
Yes. Yeah,
if
obviously. See, you
uh,
can take it, say, either take it as, for example, center frequency, or higher frequency. Okay,
Yeah.
so depends upon the bandwidth it will work, because if you have a huge bandwidth, then you have to necessarily go for center frequency, because
Yeah.
we have to cover both the distance, right? Because lambda by 4 is going to be different for higher frequency. Higher frequency lambda by 4 will be very small, okay, but
Yeah.
lower frequency it is going to be big high. That's why it's better to have a center frequency.
Yeah. Okay. So, for example, if I am investigating the phase responses based on the CST studio for different graphene chemical potential levels, it's better for me
Correct, correct.
to use the lambda by 4
Yeah,
distance and
exactly.
generate a graph
Yeah.
based on that frequency. Like, do you have some suggestions in terms of when I'm designing this material, like what kind of ratios there should be for like substrate and the thickness, or the size of the patch that should
See,
be, because these
yeah,
parameters
yeah,
affect the results a lot. Uh, so
yeah.
is there like a
So the thing is, see, hello,
yeah,
can you hear me?
yeah, I
Yeah.
can hear you.
The thing is, yeah, the thing is, no. See, the unit cell size should be lambda by 2. Okay.
Yeah,
Okay. So unit cell size should be lambda by 2. Okay. It should be square, so that it will be symmetric in both the axes.
yeah,
But if you require, you can have a rectangular also. Doesn't matter. Second thing is that substrate thickness, you have to see whether you can fabricate. It depends upon the available material. For example, if you graphene if you are using, if you can fabricate for example, 0.5 mm, 1 mm, 1
yeah,
millimeter or anything. So accordingly, you
yeah,
can consider those materials. So you have to be purely dependent on the availability. Okay, we will design some unit cell which is working wonderfully. Then after some time, when you go for fabrication, you will not find that material thickness at all. Then you have to sandwich anything, but it is going to be a trouble one. Okay, that's why it is better to have a whatever is available thickness. We will just adapt it. Then patch size perspective, you have to you can try, for example, see, there are number of wideband elements are, it is purely dependent upon your requirement. For example, you want wideband element, or one more thing I wanted to tell you that, for example, I forgot to tell you. Shall I share my screen?
yeah, yeah, of course.
Yeah. Okay. This is the last point I wanted to cover up. See, just a moment, please. Okay. So now the last point is, for example, see, you have a unit cell like this. Then you have a ground plane or reflector. Then you have patch. Okay. So just now I told that you are going to have a broadside direction. For example, it's going to plane wave is going to come over here, getting reflected over here. This is one. Okay, the same unit cell will give you different phase shifts. Okay, when you are going to have angle of incidence is like this. Okay,
Yeah,
so when you start increasing the angle of incidence, then you will see the phase variations. For example, for this curve, you are getting like this S curve. Okay,
yeah,
for this broadside one,
yeah,
you are going to get, for example, like this
mm.
also, or some kind of phase offset you will see when you are start moving ahead,
Coming from different
moving away
angles. Yeah,
from the broadside, then you are going to get, yeah. So for your application, it is very important. You have to
yeah,
see, for example, even if you have, for example, angle of incidence is 40°, still you need to get approximately, like this. Okay,
yeah, yeah,
but see, there is a one parameter called, phase bandwidth. This is plus minus 45° or 90°. Depends upon the application, we will consider this one. 45° or 90°. Which means, for example, for direct broadcast one, you are getting, for example, some point of time, you are getting, this is the frequency. For example, let's say this is the frequency F1. So for broadside direction, I am getting, for example, 220°. Let's say 220°. Okay. For offset incidence, so I have to get, within, for example, if you are considering this bandwidth, I
yeah,
have to get, for example, within plus minus 45, which means It can be from I think 175 to 175 to 265. It
Yeah.
can be. Okay.
Huh?
So if you are going beyond that, what will happen is, see, you will see someday kind of a difference in the radiation pattern. You can consider, but so there is one on paper. What is how is it, how this 45 playing a role? How see, for example, you are having a radiation pattern like this. There is an I think one interesting paper on this also. So when you start increasing the angle of incidence, so for example, you are going to compensate the phase, right, in the overall structure. For example, reflector impedance surface or anything. Okay. So here, what is happening is, see, you're going to have a phase distribution, right? So
Yeah.
what happens is, see, you are having constant phase distribution, but the unit cell is going to offer different phase shifts, right? For example, it can be 220-degree. Instead of 220-degree, I may get 265 or 195. So due to this offset, what is happening is, see, it will affect the radiation pattern. So the radiation pattern will be like this also.
It will change a lot based on the
Yeah.
incident angle.
Yes, yes. When the
So
phase offset, the offset in phase is getting widen, then
yeah.
you will get the phase because the phase distribution is getting changed, right?
Yeah.
According across the surface. That's why you are getting this kind of thing.
Uh,
That's all.
in CST, is there like
So
a
yeah, it's
um,
simple.
effective way to check how it changes based on the phase incident?
Yeah.
The,
That can definitely.
the
Yeah, yeah. See,
for
the thing is,
example,
okay. So what is happening? See, you might have studied phased arrays, right? Phased arrays, right? Okay. Spaced
yeah,
arrays are a normal arrays. Okay.
yeah,
The by applying the appropriate excitation, you can control the beam as well, right? You can broaden the beam, you can
yeah,
string, you can narrow the
mm,
beam, or you can control the silo level. So what you are doing? Indirectly, you are controlling the excitation, right? In terms of amplitude and phase. So similarly here also. So when the phase distribution gets changed, then what is happening? Your radiation pattern behavior is going to
yeah.
get changed.
The beam will change. Yeah.
Yes,
Uh,
yes. Yeah, I can. Yeah. Can you see here?
yeah, the boundary.
Uh, yeah. Yeah, here you can see.
Yeah,
So this is the distance to reference plane. You can give, for example, minus lambda by 4, whichever whatever value you can put over here. So
yeah.
here you can see that number of Floquet mode is 2 for vertical as well as the horizontal. Okay.
Hmm?
Okay. Okay. Then here you can see you can put a design frequency here. And then if you look at this one, can you see here? Theta and
Yeah,
phi, two parameters are there, right? So here
yeah,
you can see these parameters are already initiated as 0,
yeah,
initialized as 0. So you can control, for example, you can see here, if I put, for example, let's say, okay, this is the Z max, right? If
yeah.
I put, for example, phi is minus 45-degree. Okay. So
Yeah.
if you look at the here, you can see here, scan angle. Can you see here? The
Yeah.
arrow is going like this. Okay. So this is how we have to we can control this. Like, sorry, not this one. We can
So,
control the arrow.
based on this
Yeah. You can see here.
T and theta angles, I can adjust where my
So
signal
can you see?
is coming
Yeah.
from,
One
and
minute. See,
check its phase
inward.
response.
See, you
Yeah.
can have a inward, outward. Both control is there. You can see, for
Yeah.
example, minus 30, minus 45-degree.
Yeah.
Can you see here? There is
Yeah.
it's changing.
So these are in degrees, not in.
Yeah. Degrees. Yes.
But do you think the phase response is changing a lot based on the incident angle, based on what you
Yeah,
explained.
it will change, but it depends upon the unit cell design. For example, you can see here minus, for example, minus, 30 degree.
Yeah.
Can you see you can control the incidence?
Yeah.
Okay. So how it works is like, for example, I will tell you. So azimuth plane is something like this, right? Unit cell is sitting on the, for example, if unit cell sitting on the XY plane. Okay.
Yeah.
So here, for example, with respect to X, this is the X axis, this is the Y axis. Okay. For example, let's say, sorry, this is Y axis, this is the X axis. Okay. So now I can control this one,
Yeah.
5 degree. It can
Mhm.
be anything, right?
Yeah.
So here is see vertically, if you see, this is the Z axis. Okay.
Yeah.
So if I change, for example, this is the, if you look at in three-dimensional factor. So if it is same in this direction, then it will be, so I can control this one.
Yeah.
Along the X, along the Y, along
Yeah.
the Z, like that. So I can
Yeah.
control, right? I can by controlling these values, both values. Okay. So these can, you can just, view here also, no problem. You can see here.
Yeah.
So you can see here. Can you see here?
Yeah, I can see. Yeah.
Yeah, so it depends upon this. You can estimate the phase values. It's going to be same phase. Here only you're going to see, correct? Here only
Yeah.
you are going to see what is the difference you are getting. That's the only thing.
So, bitrate. It would be wrong to assume to check the phase response based on only one angle, given that you have, for example, in my UAV scenario.
Yeah. It's
Because
one angle. It's difficult. Yeah,
based
because
on the deployment, it will change a lot.
correct. It will change a lot. So
Will
this is
change a
what
lot. And
you can just
because our
estimate
aim was to actually optimize the deployment and to adjust the voltage of the graphene so that it would be best suitable for a user or like multiple users. Like that was our
correct.
thinking. But
Correct.
now that you say this,
Yeah.
creates quite a more complex problem because
Yeah. Well, see, the thing is, for example, see, you assume that it's going to be broadside incidents, right?
yeah.
But when you have offset incidents, what will happen? That point of time, that particular phase is going to be changed, right?
Yeah, and
Because
it's
yeah.
reflective amplitude and the phase would be
Yes,
changed. So you
exactly,
need to
exactly. But
have a
but the thing
huge.
is, we can have some kind of buffer, plus minus 45 or something like that. We can just evaluate. So how much changes we are getting? We will not get much changes if it is plus minus 45 degree. But if you are going beyond that, then you will get some kind of difference in the radiation pattern.
Yeah. Then of course it will be.
Yeah.
I mean that's what part of the thing that we're investigating. So it's a good, very good insight you gave.
Yeah. So no
So
problem. Yeah.
but you agree, right, that we check the S11 parameters and S11 parameters and the phase incident
Yes.
response. The CST Studio
Yes.
here is a good enough tool
Correct.
to measure and
Correct.
to understand.
Correct.
So based on one cell, then we can model it
Construct the array.
for the array.
Yeah. Because for example, those array of units, array of antenna, means RAS elements. There, the phase distribution you have to estimate from your algorithm, right? What the phase I have to introduce there. Accordingly, you can place according to the phase requirement. You can place the unit cell of different sizes. Then you will obviously get that. No problem. Okay.
Okay. Yeah, that was
That's great, actually. Yeah.
enlightening conversation.
So no problem. So you can, if you get any other further doubts, no, please feel free to ping me. I'm maybe next time, I will not, for example, I will definitely meet the promise. Okay. So thank you so much. Can you please share this recording by combining these two, and then so that it will be helpful for some other people.
Oh,
Okay.
of course, yeah, I will.